Hello. So if everyone could get their pizza and then maybe like find a seat, that would be great, as we're gonna start the lightning talk soon. So first, I want to say thank you everyone for coming today for our meetup, Ray and DeepSpeed Meetup AI at Scale. So before we get started, I would like to invite all of you to come to Ray's Summit this year. If you did not get a coupon code from me when you checked in, please come find me sometime after the lightning talks and I will give you a coupon code. We love our community and we would love to see you guys there. This is our agenda for today. We have 7 really cool lightning talks coming up. DeepSpeed, distributed training with Ray, SuperOffload, Arctic long sequence training, and a bunch more. So hopefully you guys will learn something new and have a good time.
Do we have a Wi-Fi for guests?
Yes, we do have Wi-Fi for guests. I believe we have a Wi-Fi network called Anyscale Guest, and the password is program the cloud in camel case, so capital PTC. So yeah, come find me if you can't connect for some reason. So this is our first talk, the DeepSpeed overview.
Thank you. Hi, everyone. Thanks for coming for the meetup. Yeah, okay, yes, thank you. All right, let's get, where do I point it? This to, oh, okay, just down, okay, got it. All right, so let's start with what is DeepSpeed? So DeepSpeed is an optimization library for large-scale distributed training. When we designed DeepSpeed, we had 3 key goals in mind. One was efficiency, ease of use, and effectiveness. And I think we've succeeded on all those 3 fronts. So if you train your model with DeepSpeed, you'll have high performance, whether you're running on a single GPU or up to 100,000 GPUs. Yeah, we can sort of guarantee that you'll hit high performance. DeepSpeed is easy to use. It sort of runs out of the box. And that's been one of the reasons for the success. In my opinion, it's just model scientists don't want to waste their time fighting tools and dependencies and things like that. And so it's really been good that DeepSpeed just works out of the box. Democratization of AI is another big thing that we sort of emphasize, and that means we kind of lowered the GPU budget required for you to build or use state-of-the-art AI. And it's open source. So we joined PyTorch Foundation earlier this year, and that's really been a great collaboration or environment for us to be in. So DeepSpeed itself was motivated by the early observation that scaling is what drives deep learning. Okay, and here I'm showing 2 of sort of the critical scaling dimensions. On the y-axis, you have the model size, and x-axis shows you the number of amounts of training data in billions of tokens. And so if I can just point your attention to the lower left-hand corner where we have 2018 BERT, sort of like the ground, the day 0 of deep learning till today, we've seen like a 3 orders of magnitude increase in scaling on both dimensions. And as you can imagine, the hardware folks cannot sort of keep up with that. And so this has created significant systems challenges of scaling. And so in the early days of DeepSpeed, one of the problems we tackled was was known as the GPU memory wall. And this really meant like the limitation of how the GPU memory restricted how big a model you could actually train, right? And so very quickly it was obvious that the model sizes were scaling much faster than the hardware vendors could scale the GPU memory. And to address this, we came up with 2 directions of optimizations. The first one, called ZeRO, was a technique where we ended up partitioning the model state across the data parallel ranks as a way to allow you to sort of scale your model size. And in addition, we also had the option of being able to offload to CPU memory or NVMe storage, which then essentially meant you could scale your model almost infinitely. The second direction was 3D parallelism, where we made it possible for you to combine tensor parallelism and pipeline parallelism with ZeRO. And really the impact was really great. We've had system support for trillion parameters training as far back as 2021. And also sort of a demonstration of the impacts of these techniques is that it's been adopted by pretty much every other scaling framework that's out there. They all have some version of ZeRO implemented in there. So I'm just going to talk about some of the newer directions that we've been going in since we've sort of addressed sort of the model scaling problem. So one direction is a project called DeepCompile. And the motivation for this work is that increasingly for you to be able to train efficiently, you need to integrate different kinds of parallelism techniques. And this turns out to be very difficult to do. And it's also to integrate them and also to tune them for efficiency is very, very challenging. And so with this work called DeepCompile, we've decided to sort of automate that process using compiler techniques. So we use the compiler to automatically parallelize your model. And we also use profile guided optimization at runtime to tune for efficiency for your environment. And here we've seen some really good early results there. We've seen about up to 50% speed ups over manually parallelized or manually optimized approaches. Another scaling dimension that's sort of really gotten super interesting these days is context windows. And so if you sort of go back to the early days of BERT, the context window there was about, anyone know? Anyone remember? It was about 512 tokens, and so over that period of time to now, the largest token window I've seen recently is like 100 million tokens. So we're talking like incredible scaling. So we created a technology called Arctic Sequence, Long Sequence Training, ALST, and it includes a variety of advanced tiling and sequence parallelism methods to enable scaling. So for example, on a single H100, we can actually support like 500,000 token length windows, and it scales as well. So as you add more GPUs, you just have sort of linear scaling there. So that's on the context scaling. Another direction that we focus on, like I said earlier, is democratization. And our key democratization technology is offloading. So basically, we're able to reduce the number of GPUs you need by basically leveraging your CPU memory and potentially your NVMe. And so one of the latest work we have is something called SuperOffload, where we basically are redesigning offloading for the Superchip architecture. So the traditional offloading techniques were designed for like the PCI-based, loosely coupled, but then we have this, Superchips like GH series that are coming out, and they have the C2C connection between the GPU and the CPU. And so by redesigning it, we're able to like basically achieve, up to 5x improvement over the traditional approach. We're able to eat over 50% of MFU on the Superchip, and we're able to extend sequences even longer than the baseline approach. Another work we have fairly recently as well is also tackling offloading is ZenFlow. So this one tackles the problem of the fact that when you offload to CPU, it actually stalls your GPU. So your GPU is typically idle while the CPU is doing its work. But we've observed that in the post-training scenario, the gradients sort of behave in a very interesting way. And so we leverage that, which basically is that only a few gradients are actually active in post-training scenarios. And so what we've done is we've process the optimizer computation for those gradients. We can now do that on the GPU, while the sort of slowly moving gradients get processed on the slow CPU, and that helps to just avoid stalling the GPU. And with that, compared to standard approaches as well, we've seen like a 4 to 5x speed up. So yeah, for ZenFlow. And I think the final one I'll talk about is DeepNVMe. And what this one is targeting is the fact that I/O is now like a major scalability bottleneck, right? So the models grow larger, things like checkpoint saving, data loading sort of become a bottleneck, and there we're leveraging a lot of the new storage innovations like NVMe or NVIDIA's GPU Direct Storage to basically deliver very efficient I/O for deep learning workloads. And so some of the results I'm showing here is that we can save checkpoint 20 times faster than your traditional touch.save, and you can do offloading for your generative AI. Can host like a 70 billion parameter on a single H100 and achieve fairly decent throughputs. And so those are the techniques that we have that are new in DeepSpeed today. We'll have some deep talks about two of them, the SuperOffload and the Arctic long sequence training later. So yeah, and looking forward to connecting more with you guys here. Thank you.
Thank you very much. Next, we have a talk on distributed training with Ray.
Thank you so much. Let's change that slide. Yeah, just Okay, perfect. So thanks so much for coming in here. I hope most of you have been in PyTorch conference, right? How many of you were in PyTorch conference from here? Oh, just a few of you? Okay, quite a few. Okay, so what I'm going to do now in next 10 minutes or so is just to fill you in on distributed training so that you can leverage the other speakers that are lined up and you can make the best use of this, okay? So how many of you have trained any model in a distributed fashion? Okay, few of you. And how many of you have trained any model on a single machine, maybe laptop or virtual machine? Almost everyone, right? So that's what we are going to talk about, how we can distribute a deep learning model across multiple systems. Okay, I think it's not working. Can I take that laptop here? Okay, so before Christina tells me to offload from here, if you would like to scan this, all the content is there. Just want to make sure that you go home with something new that from this meetup that you can follow on. Okay, I'll just wait for 2 seconds. Okay, perfect. So when we talk about distributed training, why we need distributed training in the first place, we have model and we have data. So these are the two things which eats up the GPU memory or the GPU, right? So these are the two things that we can target to distribute. Right? So let's start with data. And let's assume that model can be accommodated within a GPU, okay? So if the model can be accommodated within a GPU, I can add more data, right? So that's what we increase the batch size and try to keep on training. But how about distributing this data across multiple machines? Right? So that is what we are trying to do in the first place. The assumption is the model can be fit within one GPU or within one machine, okay? And we can do the training in a distributed fashion by scaling the data. We give different batch of data, different set of data for different machines. With me so far? Yes? Okay. So now let's see if we do that, how things will work. So now we need to know what is happening in the model, what is there inside the model. So inside the model, we have parameter optimizers and the optimizer states, parameter gradients and the optimizer states. So this is what we are going to have in all the machines. And now what happens is in the forward pass, we will send the data. All the machines will have different set of data passing through that model, and it will do the backward as well. And then we cannot just update the model with the loss, because in that case, we will get 4 different models. And this is why, at this point in time, we need to talk to the other machines or other GPUs, right? And this is done by the primitive based on whatever the accelerator that you are using. If you are using NVIDIA base, it may be Knuckle or whatever it is. But at this point, there is no processing happening in the GPU, right? It's the communication is happening. And then it is going to aggregate and send the cumulative gradient so that everybody can update their parameters. And at this point, all the machines are idle. The GPU is not doing anything, right? But we are able to update the parameter, and the same set of parameters is there in all the machines. And now we can again start with the new data. And this is what we call a distributed data parallel, or DDP. With me so far? Yes? So there is a problem with this, right? Because we were able to communicate, we need to communicate across the machines, but it is still okay, right? We are able to increase the throughput of our training, right? So the forward pass and backward pass, it takes the same time if I just ignore the communication thing, but the throughput increases because now I'm training in 4 machines, so 4 new batch of data I can send at the same time. So now let's see if the model cannot be fit in the machine in one GPU. What can we do? Any guess from this? The model contains these 3 things. What can we do? Anyone? Split the model, right? So let's start by splitting the optimizer. So what we can do is we have many options, as we can see here, but let's start with the optimizer. In this case, we will have the parameter and the gradients, and we will just split the optimizer. And this is what 0, 1 is. So we are not going to the details of, we don't have time now, but the forward pass and backward pass. But the common thing here is we are just splitting the optimizer states to efficiently train the model, to use the memory of your GPU efficiently, but the forward and backward pass happens just like before, okay? But it, of course, needs more communication. Now, can we further optimize? We can optimize the gradients. And this is what 0, 2 is. And what is the last thing that we can do? Anyone? Parameters. So what we can do is we can now shard the parameters. And this is what 0, 3 is, or FSDP. It depends on how we have implemented. But the point being is in all these 4 cases, we have distributed the data across different machines. And what we are doing here is each GPU is still computing the full forward pass and backward pass. It's just that when the gradients are in other machine or the parameters are in the other machine, I, as a GPU 1, I need to collect all the parameters which I needed to do the forward pass. And once that is done, I will just discard that. So there is a more communication that is needed. But from input to output, everything goes through that GPU, right? So what they do differently is the way that the model parameters are stored in different machines. So that adds a lot of back and forth communication. But still, we are able to accommodate a larger model, which we cannot fit in one GPU, right? But can we scale further? Absolutely, yes. We have different techniques like tensor parallelism, pipeline parallelism, expert parallelism, and all. There are many more options. But I just want to give you an intuition of how distributed training works in practice, right? With me so far? Yes? Okay. So now let's see how we can leverage Ray to do such distributed training. So Ray comes as a cluster manager or a distributed compute engine. And when we say cluster manager, that means there must be some cluster somewhere. So it could be on cloud, on-premise, or wherever you have your compute resources. Ray can work on top of it. And then you can either use the Ray core, which is the foundational framework, or you can use Ray Train, which is a specialized AI framework or library, which will make your training job much more easy. And that's what we are going to see next. And Ray Train can be used for PyTorch, TensorFlow, so on and so forth, depending on what kind of framework you use for your model training, inference, and so on. So let's take an example of PyTorch quickly and see how this works. So this is a distributed training vanilla code in PyTorch. It may be a little small, but the slides that you can have a look later on. But this is the function that you want to run in all the machines. This is the training function. And the next thing is you will use some parallel strategies. You have to implement or use like DDP or FSDP or whatever. So in this case, if you see the line number 8, we are using DDP from PyTorch. Right? And then we have to use a sampler because we cannot just use data loader. We have to use some distributed sampler because a different batch of data is needed in all the machines. And that's what we are doing here. And then we just run it, right? So we just run the training loop. Now let's see how things changes in Ray when you use Ray. So you import Ray Train and you import prepare model and prepare data loader because these are the two things that we were talking about, a model and the data. So you take the same model that you have, but now you pass it through prepare model, right? So now your model is prepared. Similarly, you do the same for data loader. And now you use the prepare data loader in line number 8. And the best thing is now you don't have to use a sampler. So if the number of nodes are more than 1, it will automatically use a data loader along with the sampler. So it uses a data loader under the hood, but you don't have to worry about this. So we have prepared our data and the model for distributed training, right? And in this case, it is using DDP, but you can always use different strategies. And now you have to just run it, right? You have to execute it. And for this, you just import torch trainer, and you give the training function, the function that we have written here, the same function with the prepared data and prepared model. And we just pass it here so that we tell Ray that, okay, this is the function that you want, I want to run, want you to run on every worker. And we also gave the scaling configuration, like how many workers that you need, how many GPUs that you want to run on, and so on and so forth, okay? And that's all. And you start the training, and you are done, okay? So that's how you can do Ray, you can use Ray Train to do a distributed training, okay? So if you want to learn more, you can get into ray.io, and there are a lot of sample examples, and you can go to the GitHub as well. And if you would like to know more, just send me a connection link and stay in touch. I'll be more than happy to share any resource that you would need to get started. Okay. Thank you so much.
Thank you very much. And here is our third lightning talk.
Hello, everyone. I'm Masahiro from Anyscale. I'm also a contributor to DeepSpeed. Today, now from the presentations of Tanji and Suman, now we have kind of high-level ideas about what DeepSpeed is, what distributed training is. But if you really want to start coding or the training, what should we do? Where should we start? Actually, Anyscale has a very good platform for that. Just I joined Anyscale. I really want to introduce this nice feature. So once you sign up the Anyscale platform, you see this dashboard. You can do so many things on dashboard, but today let me focus on some nice templates. By clicking here, you'll see many templates that covers a wide variety of workloads. How to use Ray for deep learning. It's not limited to only deep learning context, but you can see many workloads you can start with. But today, let me focus on this on fine-tune LLM with ray training and DeepSpeed. So if you click that, actually, this is a Jupyter notebook, but a nice part of the integration with Ray platform is just by clicking this button. So you will start a new environment for the distributed training. Actually, setting up the environment for distributed training is not very easy. Also, writing code is not very easy, but just by it is integrated with any skill platform, just by clicking a button, you can make it. But it still takes a little bit of time. It's not too long. That's like usually it's like just a few minutes. But while we are waiting here, let me explain what we have here. This is a pretty much kind of complete but simple step-by-step guide how to fine-tune a LLM using Ray, Train, and DeepSpeed. This starts with, it's a really complete guide, which library you should install, some configuration, like what model you want to train, what dataset you want to use, or some settings like DeepSpeed. Yeah, as Suman just explained, DeepSpeed has some different modes, like which we call DeepSpeed 0 stages, but you can simply change this one if you want to change the configuration. So also this notebook starts with a high-level structure of the training group. This is just what Suman explained, but here you just set up some models, optimizers, some data loaders, and then the real training starts from here. You will pick the training data from data loader and learning a loop. Then here you can run forward pass and backward pass, and then just by looping this process, you can train the model. Then the following part breaks down the details, breaks down this structure into more details, like how to set up data loader, how to initialize the model using DeepSpeed. Of course, you want to save the model once you train the model. How you can do that, how you can load the model, and some configuration of DeepSpeed. So this part is also explains some nice feature of the Ray because, for example, Ray can take this kind of configuration like scaling config. So scaling up the distributed training is sometimes not straightforward, but in this case, Ray is very flexible to scale the environment up. In this case, just by setting some numbers of GPUs you want to use, then this platform and the Ray library automatically starts the multiple processes on using multiple GPUs. And then, so if you want to train the larger model, in theory, there are many challenges, but in theory, in a very simple case, just by increasing this number, probably you will be able to train the larger model. And so that's what we offer in this template. Oh, it's still rolling. Oh, it started, but just render is running. Yeah, as this is a notebook, once you open that, and then just by clicking this, you will see how the training goes with Ray and DeepSpeed. But anyway, this is just an introduction. Yeah, if you have an interest, just sign up at Anyscale Cloud and try it. Thank you very much. Okay. Maybe next one is still mine.
Yeah, I think you need to press that.
Okay, next, let me introduce SuperOffload, a novel offloading techniques for Superchips. Compared to the previous topics, this is a little bit deeper, but let me explain. Yeah, this work was actually recently featured on PyTorch official blog, probably it was 2 weeks ago, which was really nice. Also, the research paper of this techniques will appear at the ASPLOS conference next year. What's SuperOffload? So what Suman and Tanji explained was when you want to try a very large scale model, what can we do? You partition the model and then deploy it. So partition model and then you can put into the many GPUs. But if you don't have many GPUs, what can you do? So the offloading is one of the common techniques in such situations. So you have the data on GPU memory, but you temporarily move the data onto CPU memory. But if you do offloading, of course, you can save the memory, but you will usually face low GPU utilization because the bandwidth between CPU memory and GPU memory is not very fast. If that's a PCI Gen 4, for example, it will be like 30 gigabytes per second, so which is very slow. But recently, NVIDIA released a new computer architecture, which they call Superchips. So it's now available as a server like GH200, GB200. So on that Superchip architecture, we have much faster connection between CPU and GPU memory. So it is called NVLink C2C, and the bandwidth is around 900 gigabits per second, which is way faster. So the architecture is very new and it hasn't been very explored yet, but we are trying to fully leverage that new architecture for offloading scenarios. This is what we do for this work. Then, so in summary, some of the achievement was we were able to fine-tune GPT-OS's 20B model on the Qwen 314B model on single GH200, or we trained Llama 370B model on 4GH200. Still, even though we are offloading, but the efficiency is super high, like more than 600 teraflops, which is very efficient. What we do in SuperOffload, so just to explain, let me explain the kind of traditional style of offloading. This is ZeRO offload implemented in DeepSpeed. This is already highly optimized, but what we do here is first we run forward pass and then backward pass. But during the backward pass, after you compute the gradients, you can copy that to the host memory because we update the parameters on the host memory. But only after you finish the backward pass, you can start updating the parameters. And then updated parameters is sent back to the GPU memory. But as you see in this figure, we have a lot of idle time while we are updating parameters. So this is an issue. But why do we need to wait the backward pass to complete before we update parameters? That's a question. So there are two reasons. One is we need to check the gradients. The gradients don't have any non-value or infinite values. Once you apply the Adam optimizers simply to that values, so parameters will be broken. So you cannot do that. The other reason is we need to clip gradients if the gradient value is too big. But clipping is usually doing based on the global norm or the old gradients. That's why you need to complete the backward pass before you update the parameters. But in SuperOffload, we actually do everything, we overlap everything without waiting for that gradient check and gradient clipping. Just move forward to the next word. Why can we do that? Actually, in our experiments, we found that in many cases, that check or the clipping doesn't happen. So what we are doing is we are running the parallel thread, checking the gradient values and then gradient checking. Then, so if only when we found we actually need the gradient clipping, or when we find the non-value or in values, we roll back to the previous state. So actually if you roll back, of course, it causes some overhead. But in our experiments, so we trained the Bloom model and then run 80,000 steps. But in these experiments, we found that rollbacks only happened at 93 steps, which is only almost 0.1%. So as this is very rare, it doesn't cause a lot of overhead. So we see much more benefit than overlapping everything. So then we can reduce idle time. This is the main idea, so which we call speculation then valid. In short, we call it SDV. We also applied a few more optimizations. One is superchip aware casting. So in a mixed precision setting, so where we use both precision like BF16, FP16, and the higher precision FP32. Usually backward pass and forward pass are computed in lower precision. The parameter updated down in higher precision. But usually just to reduce the overhead of data transfer, after you update a parameter, you first cast the parameter, updated parameters to the lower precision and then transfer because you need to send the less amount of data. But we found that in superchip architecture, the cast is very fast on GPU. Also, the communication between CPU and GPU is very fast. That's why we changed the strategy. First, we send the higher precision data and the cast. So our micro benchmark showed that this process is much faster on Superchip. The last one I introduced is the Grace Atom. So now Superchip architecture has a CPUs called AMD CPU called Grace CPUs. Then so we also optimized Atom implementation for that CPU architecture. So then so the final result shows that our optimized Grace Atom implementation is 3 times faster than PyTorch's normal CPU implementation. So including all these optimizations, yeah, we conducted some experiments across different models, different sequence lengths. But in summary, we observed up to 4 times higher throughput compared to prior work. Also, yeah, as I said, we able to find full fine tuning for popular 20B or 14B scale models. Also, this technology is pretty kind of universal. It is easily combined with existing techniques like DeepSpeed 03 or the DeepSeek Ulysses, which is for the long sequence training. Right. Yeah, that's it. Thank you very much.
Thank you, Masahiro. So the next talk is going to be about our solution for long context training called Arctic long sequence training. So as I shared earlier, probably the most exciting scaling that's happening right now, especially if you think about things like agents and tool use and chain of thought, is that the context window for the models is growing. So, back in 2018 with BERT was like 512 tokens was all you had to process. Today it's about 100 million tokens. So this is extreme scaling. And so that creates a challenge. How do you train models that have long context capabilities, right? That's the challenge here. So just to sort of, zero down on what that means. So let's think about what is the memory costs of long context. And that's sort of what I'm showing here for, a Llama 3 8B model. I am showing the memory consumption for the activations. And this is assuming I have activation checkpoints enabled, okay? Right, so I'm doing all that I can to minimize the memory costs. And then x-axis is showing the sequence length, y-axis is showing, activation memory consumption in gigabytes, and basically it really just blows up most linearly. And so this creates a problem. One, that on single GPUs, you can't actually, because of the GPU memory wall, you can't support greater than 32K context. We're using current techniques, right? And then there are multi-GPU solutions. So basically solutions that will parallelize your context across multiple GPUs. But those have 2 key limitations. One is that they're not compatible with Hugging Face post-training, which really is like the dominant way people do post-training these days. You grab a model from Hugging Face and you post-train. And so it's kind of a serious adoption barrier that they can't work with a Hugging Face post-training. And the second is that a lot of these techniques are designed for like multi-head attention, which is sort of like your traditional attention design. But we have some much newer ones like grouped and multi-query attention. And so, yeah, so, long context training right now has a serious adoption barrier. And so what we did with that is to build a ALST, Arctic Long Sequence Training. And so ALST has optimizations for context scaling, and there are 3 directions of those optimizations. The first is in the sequence tiling. The second is in the parallelism of the sequences, parallelizing over GPUs. And then we also leverage some PyTorch. PyTorch is constantly improving, so we leverage some of the memory optimizations in the newer versions of PyTorch. We also provided a Hugging Face post-training compatibility. So now you can use ALST to post-train today, easily. And we provide support for the newer attentions like grouped and multi-query attention. And this is just showing a shot of the results we achieved. So on a single H100, we can support 500,000 context length, and this actually scales as you add more GPUs. So let me go into some details about the optimizations here. So the first is the sequence tiling. Now, tiling is a pretty standard computer science technique. So, it's not saying anything that you probably never heard before. But the problem here is that when you're doing computation, there are a lot of intermediate tensors whose size just basically scale with your context window. Right? There's a lot of that happening, and so with things like your logits, your loss, they're all a function of your context length. And so the solution is, rather than materialize this full intermediate tensors, why not process your sequence on a tile basis? It helps to minimize and shrink that intermediate memory requirement. Now, the catch here is that this does not apply to all of your transformer computations. In particular, it doesn't work for your causal attention. Because there are cross dependencies there, right? But for your things like your MLP or loss computation, they have no cross dependencies, so you can tile away. And so here I'm showing for the loss computation for the Llama 8B. On the left is showing, this is a PyTorch memory profile, for those of you familiar with that. And it's just really just showing that when we enable tiling for the logits computation, we're able to reduce the peak memory and also reduce the total memory usage, right? The second optimization dimension is the parallelism, right? So here, let me just sort of go, we're building, the idea there is that you shard your context across multiple GPUs. And we're actually building on our prior work, which is called DeepSpeed Ulysses. And so I'll just quickly go over what's going on there. So imagine here, we're parallelizing across 2 GPUs. And so your sequence comes in, we kind of split it in half, right? And then initially we kind of projects on the QKVs in parallel on the separate GPUs. So at that point, we're sort of doing sequence parallelism. But then in Ulysses, we do attention head parallelism, right? So which is what's happening in there. And so we leverage the fast NVLinks in NVIDIA GPU to do all-to-alls, to do attention head parallelism, to compute, to process all of the tokens on all of the heads. And then eventually, as we go back to the MLP, we go back to sort of the sequence parallel mode. And so, like I said, all of this is built on the attention parallelism approach of Ulysses, of DeepSpeed Ulysses. So the improvements we've made here was really the supporting of the newer attention, because this sort of assumes multi-head attention. And I'll go into some details about what that means. So with Ulysses, this is how the multi-head attention is supported, right? So you have multi-head attention. Basically, you mean you have like one-to-one pairing between your QKV, right? And then, but we have some newer techniques like GQA, MQA, which are all trying to reduce the overhead of your KV, right? And so there's a lot of sharing going on there. Now with Ulysses, let's say we wanted to do sequence parallel of 4. It's kind of easy to do, right? You just kind of take each one of those strands and just put them on separate GPUs. But then the question is, if you have GQA, MQA, what do you do, right? Like you can't really have a good slice there. Well, the answer itself isn't so groundbreaking. It's basically we just replicate. We replicate, as appropriate, and that allows us to support all this newer attention techniques. Okay. Yep, and so then I'll just sort of jump to flash out the results that we have here, just a summary of that. So this is all on H100s, and I'm showing 3 different models, scaling the number of GPUs from 1 to 64 as appropriate. The key takeaway is like on a single GPU, we can scale your context length by 16x, right? So like I said earlier, it was 32K using standard techniques. Now you can get to 500,000 tokens. And then the other thing you'll notice is that the context windows are all scaling linearly as you add more GPUs. So we have true linear context scaling, which is really great. We've released ALST and we released an open source in a truly open source fashion in the sense that it's not just one package, but actually involved us integrating it into 3 different popular open source frameworks. So starting at the very top with Arctic Training, which is our fine-tuning framework from Snowflake, right? So we had some of the innovations integrated there. Then to Hugging Face Transformers, we had some changes there, and then eventually into DeepSpeed. And so I think this also kind of reflects like, the ideal of the open community of innovation, right? We are able to all work together across the stack to give, our community the best in the state of the art in training technology. Yep, and that's all that I have today. Thank you.
Hi, everyone. I'm Zhipeng from LinkedIn. So today I'm going to provide a quick updates of enabling the Muon optimizer in DeepSpeed. So I guess, I've been running research teams across, let's see. I've been running research team across different companies, including like Google Research, LinkedIn, and AWS. I think one of the sticking point, many ML researchers kind of, dangling around is like, how can we actually pick the right optimizer for large model training? So basically, the Muon optimizer is actually a big news a few months ago. It's actually creating a lot of stir in the industry, right? So basically, you can think about like the whole idea around that is to basically using the Newton-Schultz method to orthogonalize the 2D momentum matrix. So you can basically effectively amplify some of the rare directions, which is usually happens in like an add-on W or add-on optimizer. Because basically, like, if you look at the 2D momentum matrix, it's usually like a low rank matrix dominated by several directions, right? So basically to mitigate that, we're trying to basically incorporate this Newton-Schultz orthogonalization to actually, balance out some of the rare directions, which might play a role in like, avoiding the optimizer to attracting the local minimum. So basically, like, as a DeepSpeed projects, we're trying to create this open, it's like open implementation to basically facilitate all the ML researchers to leverage our framework for large model training. So given that, like we actually finished all the implementation and actually the PR has been merged. So now we're actually able to provide there's just like one line code change. So you can actually enable this like Muon optimizer for a variety of model training. We actually did some internal benchmarking. Basically, like you can see the Muon optimizer provides, nearly like 1.5 training speed ups. And also like, we provide multiple different functionalities, which facilitates a variety of training workloads. So, this is just a starting point. I know there's a lot of things we have to do to enable like better performance. So for example, in the thing we are trying to actually lay out for the future roadmap, including enabling this like CPU, GPU offloading for the Muon optimizer, especially for all the optimizer states. This one actually, we're going to complete it in the next maybe a few weeks. And also, like, we're trying to apply this Muon optimizer to 0 stage 3 to enable like end-to-end training support. And more importantly, like, we are going to explore some of the highly optimized version of add-on optimizer as part of the components for this like Muon optimizer. So if you look at recent like research community, right? So there's already a few research directions which are actually very exciting. So for example, some of the things we're actually seeing in the recent iClear submissions, some people actually looking at like the mixed precision, low precision Muon optimizer as the effective way to save memory footprint. So those are the directions we are actually optimizing and also exploring as well. So we welcome the developers who are interested in contribute. So to actually, raise the issue and even resubmit the PR. for this effort. Yeah, thank you so much. And all right, let's welcome Masahiro.
Thank you. Next, let me talk about DeepCompile. DeepCompile is a platform for distributed training and inference optimization at the compiler level. Yeah, Tanji briefly mentioned that, but let me give you a bit more details. DeepCompile has two capabilities. One is automatic parallelization. It applies multiple optimization pulses to rewrite a single GPU computational graph into distributed multi-GPU version. The other one is profile-guided performance tuning. DeepCompile collects profiling data at runtime to dynamically schedule computation and communication. So on the right hand, this is the overview, kind of the structure of DeepCompile. Users usually have a training script as well as the model implementation written in Python. But given the model implementation with some settings, including batch size, sequence length, and then so first DeepCompile applies a base compiler. Basically, this is PyTorch compiler to extract a computational graph of the model implementation. So it is usually represented in an intermediate representation as a graph. And then so the base compiler does a little bit more optimization, including operator fusions or something. After that, given the computational graph, DeepCompile rewrites the graph, modifies the graph. So it actually adds some communication operators into the graph. Also, it does some communication scheduling and memory optimizations. Once DeepCompiler finishes rewriting the graph, the graph will distribute it onto multiple GPUs and then run the distributed training. This is the overview, the kind of rough structure. So as an optimization example using DeepCompiler, let me take the ZeRO3. So how you can implement ZeRO3 using DeepCompiler. So yeah, as Suman already explained, the ZeRO3 shares parameters, gradients, optimizer states, everything. And then, but you need to gather parameters before you compute it at each layer. So, but we do that in using Python hook in the original ZeRO3 implementation, but in DeepCompile. So first, the left hand is the original computational graph. The parameter was given and it is computed by operator 2 and operator 3 in this graph. So, but in ZeRO3 setting, the parameter was shared. That's why you need to all gather. But the DeepCompile automatically analyzes the dependency among the operators and data. And then so it judges like, oh, we need all gather here. But also, if you all gather the data, you need a really large buffer to keep that gathered data. So you want to release the buffer as soon as possible. So also, but DeepCompile analysis, a kind of lifetime analysis of the buffer, and try to release the large buffer as soon as possible. So yeah, then so DeepCompile also has a very kind of detailed profiler, like so measuring the computation time of each operator, or the measuring the memory usage at each state of the while you're executing the computational graph. So this is an example of changes the memory usages in a kind of typical LLM training. In forward pass, typically the memory usage increases, and then in the backward, the memory usage increases a little bit, and then after keep decreasing. So DeepCompile automatically provides this kind of data and finds that in the initial stage of the forward pass, you have more available memory. So in that case, you try to launch the all-gather earlier. If you launch all-gather earlier, you need to keep the large buffer earlier. That means you need more memory. But in this case, if you find, okay, in the initial stage of forward, you can use more memory, and then you can launch all-gather earlier. That means you have more opportunities to overlap communication and computation. That's the optimization DeepCompile automatically does. Also, if it finds that we all has kind of some more memory, available memory, you also try to keep some parameters unsharded. In that case, you don't even need to launch any altogether. So everything is automatically can adjusted based on the profiling. So when we apply these techniques to some models like Llama 370B model or Mixtra, we observe some improvement. For Llama, it's 1.24 times faster. For Mixture is MOE model. It's more communication heavy. That's why you can communication scheduling worked better. And some of the examples, yeah, offloading. So offloading has a similar feature as communication in some sense because you can overlook the data movement and the computation. So in this case, DeepCompile analyzes the memory usages. Like, okay, now at this point of forward, you need this memory. So just because before this moment, we need to evict this amount of memory or something like that. So it automatically creates a plan when you should offload the data or when you should get the load back. Then, yeah, in this case, we can drastically improve the performance. Also, we apply the TEMS technology to ZenFlow. ZenFlow doesn't need a lot complicated communication strategy, but using some highly optimized implementation and a more compiler-friendly design, yeah, we observe some improvement. The one last example is we also try to apply to RL workload. And then this is not end-to-end time, but the training of actor significantly improved. Yeah, that's it. Thank you very much. Oh, sorry. Oh.
I don't need it because just one page.
Oh,
okay. Yeah, just one page. Okay. Yeah, this page I would just want to share some performance insights regarding the core binding because for the data center CPUs, we may, for example, we needed to avoid we needed to keep the data locality, and we needed to avoid the core oversubscribing. For example, if there are two sockets and we have NUMA concept, if you have triggered the NUMA remote access, there will be trigger the super long memory access latency. It will introduce a bigger performance penalty. Okay. And besides that, when we do some performance optimizations, we also need to avoid the core subscription because the OpenMP, if you open the hyperthread, the physical core will be virtualized as the two threads, and the two threads will share the same cache. For example, the L1, L2, and L3. But if you use the OpenMP, if you use distributor or two tasks within the one physical core, but just two virtual threads, it means that you will be triggered the oversubscribing due to the resource computation. So we need to avoid that. For the DeepSpeed core CPU core binding here, we leverage such kind of performance insights. We always split CPU cores for a single CPU optimize the worker and the PyTorch main threads. We need to ensure the two different computer tasks on different core sets. And beside that, we bind each rank to different CPU cores so that you can always keep the much better data locality and avoid a remote access. Okay, with that, for the speed, the ZeRO offload, we can achieve 16% performance improvement. And besides that, we also could achieve the 28x percent additional performance improvement regarding the offload. Okay, yeah, that's my point. Thank you.
And we have one more lightning talk today. Vinay was unfortunately not able to make it, but Tunji has graciously decided to cover for him.
All right. Thank you, everyone. So yeah, I am just stepping in at the last minute, so I apologize. I'm not going to do a great job as Vinay would have done. But the good news is he has an actual talk tomorrow in PyTorch conference on this topic. And so I highly recommend that you attend that. So today I'm just trying to give you like a sneak sneak tease for what he has tomorrow. So the title is how it's really talking about how in Snowflake we're leveraging Ray for our ML, for large scale ML. Now the the motivation for this is that in certain use cases such as retail, often you want to do training to forecast sales. And usually the way that's done is you end up training, you have the data, all right, which is sort of like a time series kind of data. But data is only meaningful for different SKUs of devices, right, for product sets. And so what you end up doing is you train a different model for each product, right? And that's sort of what this is showing here, where it's showing that you want to have a model per SKU, right, over the training data. And so what that means is that you're going to end up training like thousands of models in parallel, right, like on your data set. So orchestrating this is really hard, and so Snowflake has customers care about this, and so we've sort of built out a system to enable this in the Snowflake container runtime. And it's based on Ray. So it's basically a runtime environment that is optimized for data ingestion. So a lot of these models are going to be trained on large amounts of data. They're trained in parallel, like I said. The container runtime provides all of sort of the standard libraries you might use to train your model, right? And it's optimized for the data distribution on the fly, for the distributed training. It also handles things like failures that might happen while you're training. And if you're depending on whether your model training requires CPU or GPU, it automatically sort of handles that orchestration and allocation for you. And it's all sort of built on Ray, right? Built on Ray. So this kind of just shows, so the internal system is called the many model parallel training, right? So it's not large scale model training, it's many model parallel training. And so it's able to train thousands of models in parallel. And if I just kind of like zoom in here, so at the top there, we have the Snowflake table, which is the source of your data. The data is set up in partitions. The system is able to ingest all of those data in. Now, each model is going to train on a different partition of the data sets, right? And so that request gets submitted in, saying that I have this model, I want it to train on this particular partition ID. And Ray handles, as resources become available, it will handle like the deployment of the training for that model. When failures occur, Ray will kind of handle that as well. And so with that, at the bottom there, you have this different model training going on in parallel on different partitions of the data set. Yeah, and that's, I think, about it for it. So, this system leverages Ray, allows us to be able to train for scenarios where you require to train thousands of models, each of them typically small, in parallel. Thank you.
Okay, so that was all the lightning talks we had today. Did anyone have any questions for any of our speakers?
Unfortunately, I had a question on the Snowflake piece because we are right now working on it. I will just try to put across my question and maybe you can see if it's Vinay who can. So my question is, so we also use Snowflake and I believe that this is running inside the Snowpark container.
Yeah. Right,
Oh, you are from Snowflake?
Yeah.
Okay.
Yeah.
So my question is, so we are also running our services, our compute workloads inside Snowpark. So how do I use Ray to kind of say that, okay, within Snowpark, I need this much of GPU versus this much of CPU?
That is a question beyond my expertise.
Okay, cool.
I had admit that.
Would you have a way for us to get connected?
Connected Ray. So Vinay are you at PyTorch conference?
No,
you're not.
Unfortunately.
Okay. I'll connect with you and maybe get your email and then connect you with Vinay. Right?
Cool. Thank you so much.
Yeah, sure, of course.
Does anyone else have any questions? Yeah, you can just pass the mic around if anyone raises their hands, but. Oh,
Just to follow up on your original talk on ALST, you mentioned a single GPU. Is that kind of the target? And you start there and then scale with Ray, or how does that work?
Yeah. So, I mean, so usually the way we generally view optimization issues is to figure out what is the best we can do per the smallest units, which is like a GPU. And then we try to then scale linearly from there. It's not always the case that there are other bottlenecks in the way, but we find that that's having a very strong baseline, which is like your single GPU performance, is really a good principled way to know that if you're scaling linearly, right, you're sort of getting the maximum efficiency. Right? Yeah.
cool. Anyone else? Okay, well, thank you so much, everyone, for coming today. Feel free to grab another slice of pizza, come up and talk to our speakers, mingle, network, and have a great night, everyone.